Greetings and welcome to the presentation on how to use test-driven development on a QPC active object using my cpputest-for-qpc library. My name is Matthew Eshelman. I've been at this for a shockingly long number of years, hitting 30 years now. Embedded software, firmware, consulting, and occasional expert litigation support. Millions upon millions of people have used products running software that I helped design and or code. And you can learn more about me at covemountainsoftware.com. So real quick, just to give a little background, inspiration on how we got to where we are today. Samek's first edition book was super influential in my early years of writing code about 20 years ago. And just the idea of event-driven hierarchical state machines was super important to making me a better software developer in the firmware domain. And around that same time was the first exposure I had to test-driven development. The idea of writing unit tests before you write code. And I unfortunately don't remember the exact conference speaker or conference, but I do remember a quote from that presentation. Test-driven development gives you courage. And that was super important to me. At the time, I was neck deep in the world of consumer electronics, and the pressure to hit those deadlines that last 2, 4, 6 weeks before a firmware release for mass production was quite stressful. So to have another tool in your tool chest that could help give you confidence, give you courage when you're making those releases to, create millions of some widget was very important to me. But I wasn't able to put that into practice at that time. And really wasn't able to put it into practice until I read Grinning's book, Test-Driven Development for Embedded C. And that was right about the time I went to become a full-time consultant and contractor, about 10 years ago. So, and also if you're coming to this for the first time and you've never used the QP environment, just to give you a quick idea of what QP brings to the table, there's really, in my mind, it brings a whole lot of things, but the two things I want to talk about today that we're going to see during the unit testing portion of this video is event-driven active objects. And what is that? That is a thread, basically, that sits on a queue, receives an event, processes that event, and then goes back to sitting on that queue, waiting for the next event. How it processes that event could be just, a simple switch statement, but in real-world software, I have found that using a hierarchical state machine, an event-driven hierarchical state machine, is the best real-world way to go. On top of that, QP brings a publish and subscribe framework so that a active object can publish an event and not worry about who wants to receive that event, and vice versa. An active object can subscribe to events and not worry about who is emitting or publishing that event, which helps reduce some of the coupling that can happen in a firmware project. And of course, to learn more about that, go to statemachine.com and learn more. And also, if you have never run into TDD, what is TDD? It's a process of writing code, or even some people would argue designing your code, designing how that code interacts with other modules, etc. But the idea is before you write, or maybe even before you even design a module, you first start writing unit tests for that code. So you're writing tests before you write your actual target production code. And those of us who have fallen in love with TDD feel like that results in really two things: better design of the code, and it gives you that courage. It gives you these tests as an output of your development process that you can then rely on to make sure you don't make mistakes, 6 months later, a year later, 10 years later. Some of these embedded systems products out there have decade-long lifespans. So maintaining code for that amount of time without unit tests, I personally can't imagine. And I would refer you to James Grenning and his book and his articles and posts to learn more about TDD. So, as I've said, I came to appreciate and love TDD. And as part of that, in the firmware domain, came to appreciate host PC-based unit testing, which means your tests run on your host PC, not on the target device itself. And I've also just come to the conclusion that QP is one of the best ways to write firmware. So I mixed them all up and blended them all to get two different libraries that you can take advantage of: cpputest-for-qpc for the C environment and cpputest-for-qpc++. Both of these implement effectively the same thing. Today's presentation will be on the QPC version. So why did we need this library? So when you look at an active object under test, we see a lot of different ways it can interact with its environment. So if we look here on the upper left, the active object under test can receive an event posted directly to it from some external AO, or that could be from an interrupt. It could be from some other driver on the project, posting an event directly to an active object. So we need a way to do that. The active object under test could also post an event external to some other active object directly. So we need a way to intercept that or to allow that to happen while unit testing as well. The AO under test can also publish events, so it can talk to the QP framework and publish an event and not care who's receiving that. The AO under test can also subscribe to events. So again, it's just saying, hey, I don't know exactly who's publishing this particular event, but I was told that one of my requirements is that if this particular event is published, I need to react to it in some manner. The AO under test can also create timers with the QP framework. And then, of course, the framework itself can post events directly, which in this case would be any events subscribed to or timers. And then last but certainly not least, the AO under test can can call other modules or drivers directly. So we need a way when we're unit testing to observe, intercept, or simulate each of these points, each of these interaction points. And so that's where cpputest-for-qpc or qpc++ came about. So what this library does for you is since QP is open source and provides a nice clean porting layer, this library delivers a custom port of QP intended for the cPPU test and host PC based unit test environment. It's really important to note this port eliminates threads. So even though an active object in your firmware is the equivalent of a thread, when you're running in this host PC-based environment, there are no threads. And this is really important to allow the unit test to deterministically control the behavior of the unit under test. And we don't want threads running around because those threads just on a PC itself are not going to behave the same as they would on on your firmware or on your target microcontroller. So in the end, to have fully reliable unit tests, I eliminated threads in this environment. And as you'll see when we go to actually writing code, the unit test itself gives CPU time to the active object under test, effectively simulating the thread. We also have to deal with the passage of time, specifically for QP's timers. So we have a way to move time forward, which we'll see. And then there's utility classes. There's a dummy active object that allows for interacting as if there were other active objects to interact with. And there's a published event recorder that allows us to record any events published by our active object under test to then inspect those events to make sure that we publish the events we expected it to publish. And then another nice little feature, QP uses memory pools for these events when the events have data. And with various other patterns that are beyond the scope of this video, there is some risk that an active object could leak that memory pool. So at the conclusion of every single unit test, the framework checks all the memory pools to make sure all events were returned and that there are no leaks during that unit test. Okay, so our example for today is going to be a PWM service, and that's going to be our example active object under test. And we have the following requirements. It owns a single PWM, and I know that's not totally realistic, but that's an example to show what the library does for you today. And the very first thing it has to do is set this PWM to off. It's going to subscribe to a PWM on event, and this is going to come with a floating point percentage value from 0 to 1. And when it has executed that, it will publish a status indicating that the on is complete. And this particular device, the hardware engineers have informed us, has electrostatic problems. So we had to work around that. And we've been asked to refresh the PWM every 250 milliseconds. But we only have to do that when it's on. And of course, we also need to subscribe to an off event and again, publish the updated status when the off is complete. And we also have a factory test which can be posted directly to us, directly to the active object. And it only is valid when the active object is off. Otherwise, we're going to assert. And there will be a requester with a pass-fail indicator and a uint16 device ID of the PWM. So that'll be the output of that factory test. So how do we start doing this? Well, Grinning tells us very simply, you start writing a test. So we're about to go to the test environment. And that environment is going to be under Ubuntu 2204. Going to be using the CLion IDE. And at this time, it's my library's version is version 1.20, and I'm going to be testing against QPC 734, which is the latest as of today. So we're going to move to Ubuntu now. Thank you. Okay, we're in our Ubuntu environment using CLion, and we have an initial project that is seeded with the bare minimum of code to get us started on this unit testing activity. Just some quick things to point out. We have a GitHub action and workflow configured that will build and run the unit tests. And you can see that over here at the video tutorial cPPU test for QPC. And we see this nice green check mark, which is a very nice indicator that we are building and running unit tests, and those are all completing successfully. We also then have some drivers. I've already got the PWM driver initial skeleton ready to go. And it's important to note this is a C file and a C header, but cpputest runs in a C++ environment and builds in a C++ environment. So we do need to always remember our extern C header guard. When the C++ compiler encounters this header, that will be critical. So if you're used to a 100% C environment, this is something you'll have to remember to add if you weren't already. And one thing I really want to point out here, this is a driver, and this is the public header for that driver. And therefore, in this case, it is defining the interface for that driver. And you'll notice the only headers are standard compiler headers, standard bool, standard int in this particular case. There are no microcontroller specific headers included here. Ideally, the only things that should be in this header should be standard C headers. You could also, since we're building against QP, QP's header would be appropriate. Beyond that, you want to keep this as clean as possible to define a clean interface so that we can substitute in our unit test environment either a fake or a mock for that driver to allow our unit test to observe that our PWM service in this case is actually calling the driver APIs as we expect. So that's one of our observation points that we talked about in the introduction. We can take a look. So, this would be your concrete implementation in C for your microcontroller. In this case, I don't care, so I just threw some printfs in here. But we can also take a look at, and you'll notice it's in CPP, C++, that this is our substitute PWM driver, and it's making use of the cpputest mock environment. So when our unit test exercises the service such that the service, for instance, calls PWM on, the mock will register this call and will capture the parameter, percent parameter that we gave to the driver from our service. And that will allow our unit tests to observe this and confirm that our PWM service called the driver APIs as we expected. We have some externals, cpputest-for-qpc and QPC itself. I'm pulling both those in as Git submodules. We have this firmware global include file, which has things that we know all files will need access to, our BSP tick rate, and our pub sub signals. So this is the enumeration of any signals that will traverse the QP pub sub framework. And then we have our services. And you could call these different things, but I like to call them services. But these are our active objects. And we have our PWM service. It has its public header, which currently defines a constructor and a destructor and the global variable for accessing the service. And this is the pretty standard pattern of QPC projects. And I went ahead and seeded the service itself with the constructor, the destructor, and an initial state transition. But you'll notice there's no actual functionality here yet. And then we have our initial tests. this is defined in cpputest world. So to learn more about that, you do need to learn about cpputest itself. So we have a test group that I've gone ahead and defined for our PWM service. So all of the unit tests we write here will be under this test group. And I've gone ahead and created the initial setup and teardowns. And these are important to walk through. We've got the setup of our cpputest-for-qpc environment. So this is our custom port of QPC to the PC host cpputest environment. We have to basically start up QP in this case. And then I went ahead as part of my setup calling the constructor for our unit under test PWM service. And I personally like to reference in my unit test as an under test variable. So since this constructor sets the global variable here, I go ahead and just assign it here. And then we have a teardown. So after our unit test has actually executed, we will, cpputest will call the teardown. So it calls the setup first, then it calls our actual unit test, and then it calls the teardown. And this is critical because you want every unit test to be able to run independently with no dependency on previous unit tests. This is a critical feature of a unit test environment like that, where you want to make sure each test can run independently without any dependencies. If there are dependencies, that is considered an anti-pattern. Okay, so the teardown, we need to destroy and tear everything down in reverse order as our setup. So we destroy our PWM service. We need to clear out the cpputest mock environment. And then last, we need to tear down our actual faux QP environment. And I've seeded this with an initial test here. Given an it, when created, it does not crash. So since we know that cpputest calls the setup and teardown, this empty test is effectively testing the setup and teardown to at least ensure there's no crash. So we can actually go ahead and build and run this. And we see, since I built from clean and the way I have my C-line environment, it actually builds and runs all targets. So these are the tests for cpputest-for-qpc itself, and you'll only see that once when you run from clean. And then these are the tests that we're starting on for this project, and you'll see there it found the one test and ran it, and there's no failures. So this is a good starting point to move on to our other tests. And I've taken our requirements and put them in here as comments to give us an outline to start writing our unit tests, which we are going to start next. So let's do our first unit test that tests actual behavior. And we're going to focus on the startup behavior, which must initialize the PWM to its off state. So I am going to be quiet and type all of this, and we'll fast forward in the video, and then we'll talk about it when I am done. Okay, so let's talk about what we've done here. We've now written our first unit test, which confirms during startup of the active object under test that we expect it to initialize our PWM driver and we expect it to set the PWM to off. In both cases, we're returning a success value. So that's how you would test for failure results as well. And that's one of the great things about using a mock is the ability to fully control return values and the expectations around that in a controlled environment while unit testing. So we then use, exactly as we would in our target code, we create or we start our active object. So we've already constructed the active object in the setup. And now we're actually starting it, telling the quantum framework to actually manage and be able to deal with this particular active object. We do define a unit under test priority. You don't have to use that, but it's recommended that you do. And then anytime we do something with QP, we need to allow QP to run and execute a bit. In this case, it isn't actually necessary, but it's just a good habit. And in fact, it's so important. I have many combo helper methods that allow you to do something with QP and immediately process events all in one call. And then we do this because our unit test has full control over of when these active object threads actually execute. And then at this point, that thread has started. It has done whatever it was going to do upon startup. And now we can talk to the mock framework and say, please check expectations. And I've already built and executed that. And as we can see here, the mock framework is complaining, so our test failed. So now we see we have 2 tests, but one of them failed. And that's expected because I didn't actually write the code on the PWM service itself, which is what I'm going to do now. Okay. Now I have added the target code, and we now see that it builds, both tests run, there are no failures. So what you just witnessed was a reasonable form of TDD. We wrote the test first, and then we added the target code. While we were doing that, we witnessed a few things that technically violates a lot of the spirit of TDD. I went ahead and added asserts, but I have no test for those, and which required me to use in this case, we're using QP's assert, which requires us to define the source of the assert. So there's this Q define this module that you add in your C code or in your source code. And this is the header that defines the Q assert in QP. And the reason we're using Q assert instead of a C assert or some other assert is, one, the cpputest environment. This library does provide a mechanism for testing asserts, which we'll see later. So out of habit, I went ahead and threw this in here. And again, that's strict TDD purists would say that's a no-no. So that's our first test. It's now passing. So I'm going to go ahead and commit this. All right, so we have pushed that to GitHub. So you'll be able to see these commits when this video is released and follow along as you wish with the actual code. Next test, let's move on to allowing a published event to turn on our PWM. So once again, I'm going to stop talking and write the code, and then we'll talk about it. Okay, we've written our test. So you might have noticed we refactored. So the previous test represented a great helper method for starting our service under test. So that was refactored into a helper method that we'll be able to use in other unit tests. Just like your target firmware, you want to keep your unit test clean. You want to avoid copy and pasting code. And especially since a typical active object is going to have many states, or will have some number of states, you will end up with these various helper methods that drive the active object under test to a particular state or condition of interest for other tests. So just as soon as you find yourself wanting to copy from an existing unit test to a new unit test, that is a good sign that you should create a helper method up in your grouping up here, which internally that's a C++ class. Okay, so we've refactored, we've started our service under test, and the requirement is that if somebody publishes a PWM on event with a percent or percentage value, then we're supposed to set the PWM to that value. So in our we've created a new data structure. That data structure did not exist before. So this is a new event structure compatible with Q events. So it's derived using C object-oriented programming approaches from Q event. And we added this data for the percent. So this is our PWM service on request event. We allocated that using QNew, which means it'll be pulled out of an event pool. And we set that percent value to our test value. And then we said, hey, mock, we're expecting somebody to call PWM on, and we're expecting it to call it with the parameter for percent of this percent value, and we want to return a success value. We then, this is one of those helper methods I mentioned earlier. This will publish that event and immediately give processing time to the framework to go ahead and process any resulting events that went to any active object. But obviously in this case, our active object under test is the primary concern. And then we check expectations. And just like before, our test is failing. We now see that we have 3 tests and the test is failing. So now we are going to go write our code for the PWM service that actually implements what we're testing here. Okay, so we've written the code, and we might have expected this to pass, but it's failing. So the question is, why is it failing? So we go look at our test, and we're like, you know, I've set this value, I've newed it, I've published it, I've given processing time, and nothing happened that we expected here. The call was not fulfilled. And then we remember, it's like, oh yeah, we published this event into the framework. Well, that means our PWM under service needed to have subscribed to that event, and I forgot to do that. This is very important. This is one of the reasons. I wrote this library as well. Is you might be tempted in a more direct way to just directly post that published event. But if your requirement is to react to it as a published event, then that is what your unit test should ideally test. So if you allocated this event and then directly posted it to your method under test, you would still accidentally forget to actually subscribe to that event. So by using this cpputest-for-qpc, by using this publish and process, we are testing the full set of requirements related to this event, i.e. that it is to be reacted to when published by other entities in our firmware. So now we'll add that code. And voila. Now that we are properly subscribed to the PWM request on signal, the code that we wrote earlier does in fact work and now passes the test. So let's commit this. And then we'll work on our next test. Okay, next test. I am going to continue to ignore the publish status events for now. And this one looks interesting to me. So let's work on this. And again, I'm going to go silent and write the code and come back and discuss it. Okay, so as before, I took the previous test where we activated the service to its on state and turned that into a helper method, anticipating the fact that I'm going to want to have several unit tests that need to start with the service already in its on state. And we used that, and we, just for fun, I changed the test percentage used. And then using the mock framework, I prepared us for another on with our, this test percentage, and used our cpputest-for-qpc helper method, move time forward, which moves time forward and processes events with every tick. To simulate the forward movement of time. And then I checked expectations. And since we didn't write any code, as expected, the test failed. So now we're going to go write the target code. Okay, so astute observers will notice I meant to have this set to 1,000 ticks per second at the beginning of the project, but forgot to change it. So to achieve the 250 milliseconds, we do need to achieve it precisely. I did want this at 1,000 ticks. So that would impact the entire firmware project. So you wouldn't do that in a TDD sense unless you felt safe and had talked with the team to make sure that didn't impact anything else. But I did mean for this to be at 1,000, so I changed it. So what we ended up doing here, so first off, we now have 4 tests. They're all running. There's no failures. So we are passing. So time did move forward. The timer did fire. Per QP, we need to have our kind of internal signals, which we always start at the end of the pub sub signal range. One of my recommendations for a lot of firmware projects is that each service gets assigned a range of signal values. This just makes it easier for humans and logging, debugging, and just kind of creates an easier to understand range when you're looking at logs. But for this purpose, this is the minimum requirements to make sure you're outside the pub sub signal range. And I went ahead and defined a constant. We need 250 milliseconds, so I just quickly did it that way. There's probably better math here that we could do, but we're going to leave it. And per QP, we have to construct our timer event. So that's what we did here. We added it as a member to our PWM service class, effectively. So it's a member variable, refresh timer. And we made sure to call the constructor for that in our initial. And then we armed it in the entry. And just out of habit, I went ahead and disarmed it in the exit. Otherwise, that timer would still be firing when we transition back to off, which would be a waste. And then we added the handler for it to refresh the PWM with the current percentage. And I went ahead and left that assert pattern in here, and we handled the event. And as we showed over here, we moved time forward, and that call actually did happen. Oops, sorry, wrong code. Yeah, move time forward. Now, at this point, you might go, well, am I actually doing this every 250 milliseconds? So if you're in the, it wouldn't hurt to go ahead and copy that one more time, and we can then see that indeed we are still moving time forward. So now, is this really working? I mean, is there something fancy, weird going on? Let's make sure that, so we'll just move forward 240 milliseconds. And sure enough, it now fails. So we did not quite make it to the 250 milliseconds. And I mean, it should work down to the millisecond. And sure enough, it still fails. And now it should go back to passing. And there we are. So this is, one of the nice features of this cPPU test for QPC is this ability to move time forward. And of course, since this is running on the host PC, that happens, nanoseconds or microseconds. So it happens super fast, which is very nice. In fact, as you can see, these 4 tests ran, it couldn't even measure the time. So it's, super fast, which is a nice feature. So let's commit and push this. Okay, time for another test. Okay, I feel like taking care of this one next. And this is going to be pretty similar to our other off to on transition. So now we're going to want to test on to off. So I'm just going to be quiet, write code, and then we'll talk about it. Okay, so this, well, let's see what happens here. Okay, as expected, this fails because we haven't written the target code for this yet. So we just, we declared our new pub sub signal request off, and we expect PWM off to be called. We're using our handy helper method to get us into the on state. And then the cPPU test for QPC provides a handy publish and process where you're just publishing a event without any data. So this is a trivial event, PWM request off sig. So there's a helper method that publishes an event with this signal into the framework and then gives processing time to all the active objects present at that time. And then, of course, we're doing our check expectations. As we see, the test fails, so now we write our target code. All right, so once again, we're failing, and once again, I forgot to subscribe. And voila, we are now passing 5 unit tests. And look at that, we now suddenly measured a full millisecond for all those tests to run. Commit Okay, time to move on to the next test. Okay, I think we have procrastinated long enough. So let's go ahead and take care of looking for some published events from our active object under test. So we have these requirements that anytime we turn the PWM off, we publish an event, and anytime we activate it and turn it on, we also publish an event. So let's take care of this off. I'll be quiet for a little bit and then explain the code I've written. Let's talk about this real quick. So I've just created, this is a factory method that creates and starts a published event recorder. So a published event recorder is an active object. So at this point we have our active object under test, and we have this event recorder as two separate active objects running in our, our ported quantum framework, QP. So I'm going to hit build, and we're going to see lots of scary things. All right, so first off, we see a leak was detected in an internal event pool. So the event recorder actually subscribes as an active object to all the pub sub signals, hence why we provided this starting value and end value. So it is an active object, and it has subscribed to everything. When it receives an event, it is more or less following the deferred event pattern, and it's just putting that event aside internally for retrieval from our unit tests later. And it records all the events received, first in, first out. Now, so we're getting these leak detects because this recorder is now running, and it is recording and deferring events, and we're not pulling those out anywhere. So there's a couple of things here. We really don't want to record events that we are publishing from the test itself. So we need to find all these places that we used publish and process and give it the recorder. If you provide a null, it doesn't do anything. But if you give it a pointer to the recorder, within this publish and process, it will purposefully ignore the event that you are about to publish. And so we need to do that in each of the places that we are publishing in here. And then we can run our tests. Now, we don't have any memory pool leaks, which is a feature of cpputest-for-qpc. Now we have another memory leak, and that is actually from cpputest itself, which has detected the fact that up here in our setup, we allocated memory, because if you look at this code here, there's a new, so it's allocating memory, but we didn't delete it. So we need to remember to delete in the teardown our recorder. And now we are back to where we would expect to be. All of our unit tests are passing. So now I'm going to go back quiet, and we're going to actually use that recorder in a new unit test. Okay. So why am I getting a seg fault? What's going on here? Ah, I know what's going on. Sorry. Let's okay. So since our unit under test is actually not publishing this signal yet, when I did the get recorded event from the recorder, that unique pointer object there is actually null. So when I wrote that is_off_sig equals to the event sig, that event pointer was null, so that resulted in a segmentation fault. So we needed to add a check true that this was not a null event. And now we get that failure, which is what we expect since we haven't written the code on the unit test itself yet. Now, you'll also notice, rather than creating a separate new unit test for this, since this is tied intimately into that transition to off, we need to just go ahead and put this in our helper methods here. So we know that start service under test always goes to off. So for now, this event should always be emitted every time the service starts up. So this was an appropriate place to add this. We're going to add code to the target now. Okay, we added our publish. So anytime we enter the state of off, we set the PWM to off. It survives the assert, so we can tell the rest of the system and any other active objects that may be curious about this change that we have, in fact, set the PWM to off. All of our tests pass, so that's a good sign. But we should, we know we wrote another unit test that checked here. So we should really be confirming this here as well. All right, and we've now confirmed that that was published as expected in this test as well. So we feel pretty good about this. We also need to do the on event. So I'm going to go ahead and handle that right now as well. Okay, as before, this event is not actually being published yet because we haven't written the target code, but we now have our failing test. So now we can go add the target code. And there we go, tests are passing. I was going to add a data element to this, but this video has gotten longer than I had in my head. So I will leave that as an exercise to the reader. So if you are interested in doing that, feel free to clone this repository, get it set up, run it, and change this from a static const event to a queue_new event, and confirm that the current percentage is reflected correctly in a status event. So you would have to create an event data type structure for that, and put that floating point percentage into there, and add that and modify the unit test to reflect that. See how that goes for you. Okay, let's commit. And let's move on to the next test. We are down to our last requirement or set of requirements related to performing a factory test request. This requirement's a little different than the pub sub ones we've looked at because for whatever reason we decided that this would only be through a direct posting mechanism, and the response would also have to be posted back to whoever asked for it. Because of this, we will need to make use of another feature of the cpputest-for-qpc library, which is a dummy active object. So this test is going to be a little more complicated looking by the time we're done, since we're going to have to create this dummy active object and make use of it. And each event going to and from is going to be carrying data so that the PWM service can respond. So it'll at least need to know who to respond to. So that'll have to be a piece of data along with the event. as well as, of course, the results on the response. All right, so here we go. All right, let me pause real quick and just explain this real quick. So we just defined a new event type, but we also needed a signal value, an enumeration to identify that event. And we didn't have one, and we didn't even have in our public header file yet the concept of signals that are meant to be posted directly to this service, to this active object. So we added that, and we keyed it off the max pub sub signals, which means we don't want this to overlap with the internal signals that we had already defined, so we had to add this max posted signals and key off that over here. This is one of those, you want to make sure all your signals values are distinct ideally across all of your active objects, just to avoid any confusion. All right, back to coding. Okay, we have completed our unit test. This is a complicated one, so we're going to talk through it. As you can see, it is failing, which we would expect since we haven't actually written target code yet. So we had to create this dummy active object, which is a feature of cpputest-for-qpc. It's a utility class. I need to create a factory for this. It's a little tedious to do this in 2 steps using a little more advanced C++ here, but I'm using the unique pointer to ensure that this dummy object is destroyed at the end of this test. So C++ will take care of that for me. I go ahead and start it. It does need to have a unique active object priority, just like any active object in QP. So I just do our under test priority -1. That's another thing I probably should add is a few of these handy ones for dummies as well. And then we need to post a request. So I went ahead and typed this up, and then I went and created this event. So that was some module level code I had to write in response to this test. And then I set the members. So this is the active object requesting the test, and this is the response signal that we want used when the service posts its response back to in this case, the dummy. So I just, used a fairly random number outside our pub sub range. Didn't really think about it too much. And then I posted it with this signal, of course. I'm posting it to our active object under test, and before that I'm expecting it to execute the PWM factory test. So here we check expectations, and that's where our test is failing at this moment. If it had somehow gotten past that, it would have failed on one of these checks later. In response to the factory test, we expect an event to be posted back to the active object making the request, in this case our dummy, and we set up the dummy as a recorder. So we just simply say get the recorded event, And we checked that the response sig that we asked it to use was in fact the one used. And then we have to cast to the exact expected data type. So this is when we had to create another data type. So we created our request data type, and here's our response data type, event data type. And we added a test passed and a device ID field. And here we checked that we did in fact get the expected device ID and that the test did in fact pass. So this test is now ready for target code to be implemented. So here we go. Okay, we finished our target code. The target code casts the incoming event into our event-specific data type. It executes our target PWM factory test, which, if you look at the comments for that, notes that 0xFF is a test failed condition. Otherwise, any other value is a valid ID and a pass. So we have to allocate our response event, and we use the signal that the requester asked us to use, so that it's a signal value that fits within their range. And you know, I just went ahead and wrote this code now. In the spirit of TDD, I can, once I have all my tests passing and committed, I can come back and refactor this later if I so choose to. And I should choose to. Device ID equals device ID. We post it back, boom. And since we already had all those tests written, everything passed. We now have 6 tests running and all passing. So let's commit this. Okay. Okay, we are down to our last unit test that I want to use to demonstrate, in this case, 2 different features of cpputest for QPC. So I'm going to dive right in, and we're going to focus on the fact that if somebody asks for a factory test request when the PWM is on, it is supposed to assert. So here we go. Okay, we have written our first test. For testing in assert, there is a special header that you can include that has some facilities already prepared for you in this qassert mock support. So we're specifically, since we're working with QP, we're using their assert, which is, you know, handy for various other reasons outside the scope of unit testing. So this goes ahead and prepares the mock framework for that assert. And in this case, we have a generic any assert. If you really want to test, you know, the exact module and ID that was communicated with the assert, then you can also do that. I tend to just test the assert itself, and that way the test doesn't become too tied to this level of detail. But there are certainly cases where that would be important to your product development cycle. Okay, so we've written our test. We are saying we're expecting assert. We've posted. I don't care about these exact values, but I went ahead and set them to something reasonable. But they're not actually going to get used in this test. And the test fails as we expect. So let's write the target code. Okay, so we added our assert and into our target code in the PWM service itself. And now we're getting kind of a funny, perhaps unexpected result that I want to talk about briefly here. So the test is being marked as failing because it says a leak was detected. Since our test is allocating an event and an assert is happening in the middle of the processing of that event, and the assert, the implementation of this assert in the cPPU test for QPC, it does talk to the mock framework, but in order to ensure that the assert truly interrupts processing, just like a real world assert, it uses a cpputest C++ exception, which is thrown to interrupt processing. So this allocated event is detected as a leak at the conclusion of this unit test. So this is a false failure. And now I'm going to show you how to deal with that. All right, so we have this change memory pool teardown option, which you can set on a per test basis. So now we're just telling the cPPU test for QPC to ignore memory pool leak detection during this unit test. So now, et voila, 7 tests, 7 ran, no failures. And with that, we have written our last unit test. I do want to emphasize that all of this was contrived, of course, to demonstrate each of the features of cPPU test for QPC. The PWM service code itself, there's plenty of things we could improve upon, from magic numbers to checking for ranges on the test percentage supplied, or maybe even check to make sure this is a valid range. There's plenty of additional error checking and better things we could do in that code. But the focus of all these tests was cPPU test for QPC. Well, congratulations. If you made it through this entire video, you have now seen how to use the cPPU test for QPC unit test support library to do host-based unit testing of your QP-based firmware. Specifically, we interacted with a driver interface and tested that using mocks. Our active object under test reacted to externally published events. We also verified using published event recorder events published by our active object under test. We tested the passage of time to observe our active object under test reacting to time, specifically through QP's timers. We verified events posted by the active object to other external active objects using a dummy active object. We also were able to unit test QAssert usage. And we noted and talked about the fact that the cPPU test for QPC includes QP memory pool leak detection. So every unit test by default checks for leaks in the QP memory pools. And we talked about how to disable that leak detection for particular cases, in particular when you're testing for asserts. So that was, I think, all the features of cPPU test for QPC. To learn more, I did not obviously turn this into a tutorial on QP itself. There's just a wealth of information at statemachine.com. If you would prefer on-target unit testing so that you don't have to worry about mocks and making sure you have clean driver interfaces, QUtest is available, and you can learn more about that also at statemachine.com. To learn more about cPPU test, there's their website. To learn more about TDD and unit testing generally for firmware, C projects, check out James Grenning and his website, wingmansoftware.com. And to learn more about my consulting services, you can check me out at covemountainsoftware.com. I am available for consulting and helping teams transition to using QP. It's one of my favorite consulting gigs to do. So feel free to reach out. Thank you very much.